Hi everyone, welcome to this lesson on Unit 8, Fluid, Electrolyte, and Acid-Base Imbalances. This is Part 1. Part 2 and 3 will follow. In today's lesson, we're going to go through the pathophysiology of fluid disorders. Specifically, we'll look at hypovolemia, clinical dehydration, and then we'll switch to the pathophysiology of hypovolemia, look at edema as well. Please remember to read chapters 24 and 25 while always referring to the learning outcomes in the syllabus. In addition, please make sure that you do know the normal physiology of fluid balance that we covered in A&P2.
So we'll start off by looking at the function of the body fluids. And yes, the main body fluid is water. We'll talk about the percentage of body weight that water takes up and so forth on a different slide. But here we're just talking about the function of water essentially. So water acts as a solvent, and the solvent means that it's simply that all the electrolytes, basically everything, dissolves in water. So all the chemical reactions, including all the enzymatic reactions, all occur in the solution phase, and water is the solvent. In addition, if you're talking about blood, and remember plasma is made up of essentially water, plasma therefore enables the transport of oxygen, nutrients, hormones, chemicals, waste products, etc. So all that is essentially dissolved in water, including oxygen, and yes, oxygen will ultimately bind to hemoglobin, but all the others essentially are dissolved in plasma, and plasma is essentially water with a few other components. We have thermoregulation, so that's the function of the eccrine sweat glands. When we have sweating occurring, water will evaporate on the surface of the skin, thereby releasing heat and bringing down body temperature. That's all homeostasis, which we learned in A&P1. So let's talk about fluid homeostasis. Naturally, the amount of water entering the body has to more or less equal to the amount of water leaving the body. That's homeostasis. So we can't have an excess of fluid, or we can't have a deficit of fluid. So let's briefly talk about fluid homeostasis or water homeostasis, and then we'll describe it in more detail as we move forward. So in terms of the intake, we have fluid intake, which mainly comes from drinking of beverages, and hopefully that's mainly water rather than pop. But fluid intake can also occur via an IV, as you can see on the right. And essentially that's more or less the extent of our fluid intake. We will see that we also have fluid production via general metabolism, right? So whenever we metabolize glucose or any other nutrient for that matter, we always produce water as well. So, and in addition, when we do aerobic respiration, glucose plus oxygen will give you ATP plus carbon dioxide plus water. So don't forget that we also generate endogenous water. Endogenous meaning within the body itself we produce water. So not all of our fluid intake comes from beverages. We also produce water through metabolism as well. And so we'll talk about fluid distribution, etc. later on. Let's talk about fluid losses. So fluid can be excreted through insensible losses from the skin and the lungs. Those are called insensible because you really don't notice them. So we're talking about sweating, and our breath is vaporized. So we humidify the air coming in, and then when we exhale out, we lose some water in the humid air as well that we exhale out. And so those are some losses over there, and we'll see exactly how much those losses amount to. So after fluid intake, after drinking a beverage, obviously we have fluid absorption in the intestines, and then we'll have fluid excretion through the kidneys and through the bowel as well. So we always remember urine, but we don't remember that we lose a couple of 100 mils of water through our intestine through feces generation and then excretion. And suddenly during states of severe diarrhea, you can lose a lot of water in that manner because we're not absorbing the water from the large intestines. Remember, the function of the large intestines, or one of the main functions of the large intestines, is to absorb water. And if the transit time through the large intestines is very rapid, as in cases of diarrhea, then you're not going to be able to absorb as much water, and you're going to have very loose feces and stool, and that's going to enable the loss of a lot of water through diarrhea. There's also fluid loss through abdominal routes, which we won't talk about, but any sort of drain that's placed, especially in the abdominal cavity, will enable loss of peritoneal fluid, and etc. And so that's the losses. So we'll look at the losses and we'll look at the intake in more detail, but essentially fluid intake has to equal to fluid loss. in order to maintain homeostasis. We'll start right at the beginning, and let's talk about the composition of water in our body. So we have total body water, which is abbreviated as TBW, which makes up 60% of our body weight in men and approximately 50% in women. And that's because women typically have a higher percentage of fat. The percentage of total body water does decrease with age and increasing obesity. No surprise there, because obesity means an excess of fat, and the fat essentially displaces the water. Let's talk about the distribution of water. In P, we learned about the ICF, or intracellular fluid, and the ECF, or extracellular fluid. The ECF, in turn, is made up of plasma and interstitial fluid. The ICF is all the cytoplasm, right? All the cytosol, everything within the cells. So the ICF makes up 2/3 of total body water. So 2/3 times 60% in a male would make it intracellular fluid making up 40% of our body weight. In terms of ECF, ECF is 1/3 of total body water, or 20% of body weight. And now we can break up ECF into two components: plasma, which is 1/4 of the ECF, and interstitial fluid, which is 3/4 of ECF. I'll leave it to you to figure out the math in terms of body weight and total body water. Essentially, it's 1/3 times 1/4 for plasma, so that's 1/12 of total body water. And for interstitial fluid is 3/4 times 1/3, which makes it 1/4 of total body water. So you should know the distribution of fluid within these various compartments. Let's start with our actual lesson over here. So firstly, how do we assess for volume status? How do you know if someone is volume deficient or in a state of volume excess? So assessing volume status is actually not a simple task, as you might imagine. You might have learned in your health assessment classes about skin turgor and mucous membranes, but those are actually rather difficult to assess and are not always reliable indicators of volume status. Obviously, if the mucous membranes are very dry and skin turgidity is slack, and then you could probably guess that the volume status is deficient. Nevertheless, or hypovolemia has occurred. Nevertheless, it's not always reliable. So in fact, it turns out that the best thing in an inpatient to monitor volume status is actually daily weights, because we saw that water, or total body water, makes up 60% of body weight. So if you're constantly losing fluid, then your body weight should decrease. So it turns out that that's probably one of the most accurate assessments of volume trends. So we're talking about trends, right? That's what's important over here. It's also important to know what typical urine output for adults are. We're only going to focus on adults, not the pediatric population over here. And for normal urine output for adults, it's about, we'll just round it up, about 1 ml per kilogram per hour. So again, I'll leave it to you to do the math for a typical male and female. For about the prototypical person is a male, 70 kilograms, etc. So you can work out typically how much urine output in a day that should be. So let's look at the various factors that influence body fluid distribution. And all this is actually a review of Chapter 19 in ANP2. So in Chapter 19, we learned about capillary exchange. That's exactly what we're talking about over here. So we know there are two compartments in the body, two main compartments: the ICF, all the fluid within the cell, and then the ECF, which is divided into the plasma, everything inside the vascular compartment, and the interstitial fluid over here, right? So it's 2/3 ICF, 1/3 ECF, and in terms of ECF, 1/4 of ECF is plasma, 3/4 is interstitial fluid. So now we look at the various forces that are operating in terms of the movement of water in and out of the cell towards the ECF, and then within the ECF itself, how is it distributed between plasma and the interstitial fluid. It all has to do with osmotic and hydrostatic pressures. So we'll start off with looking at the cell over here. So within the cell, we have intracellular fluid osmotic pressure, because there are a lot of proteins within the cell, as we all know, right? So that's the main force that is driving fluid into the cell, is the osmotic pressure. As opposed to in this interstitial fluid, which is really very protein poor, there's not much osmotic pressure, and so that's not going to drive fluid into the interstitial compartment. Nevertheless, there is hydrostatic pressure over here. So in essence, water is moving in and out of the cells, but it all depends upon the osmolarity. At equilibrium, at homeostasis, the osmolarity of the fluid within the cell and outside the cell is equal, so there's no net movement of water. Water is still moving in and out, but at the end of the day, there's no net movement of water into or out of the cell. So the cell is not going to shrink and the cell is not going to expand. This is all osmosis. So let's look on the other side over here between the vascular compartment and the interstitial compartment, and this is probably more important. We have several forces again operating: hydrostatic pressure and osmotic pressure. Firstly, we have capillary hydrostatic pressure, so that's just really blood pressure that is pushing fluid out of the capillary into the interstitial fluid. So that is significant, and so water is constantly being pushed out of the vascular compartment into the interstitial fluid. Now, if that occurred exclusively, then pretty soon the vascular compartment would collapse because there'd be no fluid left in the vascular compartment. So what brings the fluid back into the vascular compartment? And that is the capillary osmotic pressure. So within the vascular compartment, we have proteins like albumin, we have cells, etc. So that generates a significant osmotic pressure, and that draws the pressure fluid back into the vascular compartment. So there's a balance between the capillary hydrostatic pressure and the capillary osmotic pressure working in opposite direction. In terms of the interstitial hydrostatic pressure and the interstitial osmotic pressure, there's really not much, so we can ignore that. There has to be a balance between our capillary osmotic pressure and capillary hydrostatic pressure. So if capillary hydrostatic pressure increases, more fluid is going to be pushed out of the vascular compartment. As you can imagine, in states of hypovolemia, there's going to be a lot of fluid, say excessive IV infusions, you're going to be a lot of fluid in the vascular compartment. That's going to increase capillary hydrostatic pressure. Fluid's going to be pushed out of the vascular compartment into the interstitial compartment. On the other hand, during states of hypovolemia, where there's very little water remaining in the body, when we say very little, we're talking about relatively speaking. Obviously, there can be zero, but relatively speaking, if there's less water in the vascular compartment, hypovolemia, now capillary hydrostatic pressure will be less and less fluid will be pushed out of the capillary. Similarly, osmotic pressure in the capillary is really essentially based upon the protein content in the vascular compartment. So if we have, say, any sort of liver disease, and the reason why we're focused on liver disease is because the liver produces albumin. And if the liver can no longer produce albumin effectively, now that the albumin content in the blood vessels is going to, or in the plasma, is going to decrease, and hence capillary osmotic pressure is going to decrease. Less fluid will be pulled back into the capillaries and more fluid will be left in the interstitial compartment. Is it any surprise then that one of the clinical manifestations of any liver disease, such as hepatitis, acute hepatitis, or liver cirrhosis, one of the main clinical manifestations is edema? And that's because there's less capillary osmotic pressure due to a decrease in albumin synthesis. So we have a hypoalbuminemia, which means simply a lower concentration of albumin in plasma. Hence, less water is going to be pulled back into the capillary and more water is going to be left out in the interstitial compartment. That's edema, right? So it's really all about a balance between capillary hydrostatic pressure and capillary osmotic pressure. Please make sure that you revise all these concepts from chapter 19 in A&P 2. So how does the body really assess whether it is in a hypovolemic or hypovolemic state? So hypovolemic meaning too much fluid volume, hypovolemic meaning too little fluid volume. Well, that is determined by the osmoreceptors near the hypothalamus. So in the hypothalamus, we have these various osmoreceptors that monitor the osmolarity of the plasma over here. So when the osmolarity is within the normal range, these osmoreceptors are quiet essentially, and no action potentials are then generated. During states of volume depletion or during hypovolemia, now the osmolarity of plasma will increase. There's less water, and hence, assuming all the other proteins and cells all remain the same, the concentration of plasma is going to increase, the osmolarity rises, and hence the osmoreceptors will be able to detect it. Essentially, water moves out of these osmoreceptors via osmosis, as you would anticipate. The osmoreceptors shrink, and that in turn is a trigger for generating action potentials. So we'll see where those action potentials get sent. Essentially, they get sent to the hypothalamus, and we'll see how the hypothalamus responds. This is essentially how the hypothalamus responds. So we're monitoring ECF osmolarity. That's the variable. The osmoreceptors, this is all homeostasis, remember? So we need to have a receptor that's osmoreceptors near the hypothalamus. So if the ECF osmolarity increases, during states of hypovolemia. That will be detected by the osmoreceptors near the hypothalamus. They will shrink, they will send signals to the hypothalamus, and here's the outcome. Here's the effects. So these are the effectors, so to speak, and that's the outcome. So what the hypothalamus will do is that because ECF osmolarity is increases due to hypovolemia, we now need to retain more water. So the posterior pituitary releases ADH, and we know what ADH does, right? Antidiuretic hormone. We learned that in ANP2. So please remember that you need to go through all the hormones in ANP2, specifically related to fluid and electrolyte homeostasis. So ADH is certainly involved in fluid homeostasis. So ADH is the hypothalamus signals the posterior pituitary to release ADH. What ADH does is that it increases the synthesis of the aquaporins and inserts them into the collecting ducts in the kidneys, and as a result of the collecting ducts in the nephrons in the kidneys, and as a result more water is absorbed from the collecting ducts. As more water is absorbed from the collecting ducts, ECF volume would increase and ECF osmolarity would decrease, and there you have a negative feedback effect working on the osmoreceptors, right? On the at the same time, the ADH also stimulates the water retention, as we already mentioned, in the renal collecting ducts, and that increases ECF volume. So what about this ANP? The ANP actually operates in the opposite direction. So you can think of ANP as the exact opposite of ADH. ANP operates during states of hypervolemia. So during states of hypervolemia, the osmoreceptors will start swelling. They will signal they would increase ECF volume. So ECF volume is really first increase, and then ECF osmolarity will decrease. Osmoreceptors will start swelling, and as a result, due to the increase in ECF volume, that is detected by the blood flowing back into the atria in the heart itself, both the left and right atria, because we have increased blood volume, right? That's what ECF volume is. An increase in ECF volume is an increase in both of the volume in the interstitial fluid and plasma. So that's going to really mean an increase in blood volume. That's going to be detected by the specialized atrial cells in the heart, and that will cause a release of ANP. ANP, as we'll see, will now inhibit the release of ADH and inhibit or increase water retention in the renal collecting ducts, right? So these two hormones work opposite to each other. It's a seesaw effect. As ADH increases, it will increase ECF volume, then ANP increases, that will cause ADH to decrease in volume, right? So they work in opposite ways, and that's why you see this negative signal over here. It's a negative feedback effect. As ADH is increased, as we went through initially, ECF volume increases. That will in turn trigger ANP release. That in turn will trigger less ADH being released, right? In addition to the osmoreceptors negative feedback over here. So basically what it comes down to is that in states of hypovolemia, more ADH will be released. And in cases of hypervolemia, ANP will be released to atrial natriuretic peptide that will bring down fluid volume. So in cases of, once more, in cases of hypovolemia, ADH will be increased, and hence ECF volume will ultimately be increased due to increased water reabsorption in the renal collecting ducts, and that's how it works for hypovolemia. In cases of hypovolemia, ECF volume and plasma volume will increase, ANP will increase, and that will cause a decrease in ADH, and that's how you bring down volume in the body, right? So make sure you know the actions of ADH as well as ANP. So once more, let's go through the various steps over here and bring in a couple of more hormones, especially in cases of hypovolemia. So ECF volume falls, that's hypovolemia. What exactly happens? Well, we've already talked about the osmoreceptors, so we're not going to talk about that, but essentially here it is over here, the osmoreceptors. Right? The osmoreceptors, which are a form of a baroreceptors, really, the osmoreceptors will signal the posterior pituitary to release ADH. ADH will cause increased water retention, ECF volume rises. That's great. But there are other pathways that also operate in terms of increasing ECF volume when ECF volume falls. And that will be the renin-angiotensin-aldosterone system. So please make sure that you revise through. We went through the RAS cascade, the renin-angiotensin-aldosterone cascade, in great detail in ANP2 when we did the chapter on the urinary system, so please make sure you revise that. But essentially what happens is that when ECF volume falls, there is less fluid going through the glomerulus, specifically the afferent arteriole in the glomerulus. The macular denser cells realize that there's less fluid being released, hence renin will be released from the granular cells in the afferent arteriole. Renin will trigger the release of angiotensin 1. Angiotensin 1 will travel through the bloodstream and be converted by the angiotensin converting enzyme to angiotensin 2. Angiotensin 2 is a potent vasoconstrictor, which will increase blood pressure, but it also causes sodium retention. It does so a little bit on its own, but angiotensin 2 also stimulates the release of aldosterone from the adrenal glands, and aldosterone is the main hormone involved in sodium homeostasis. So aldosterone increases sodium reabsorption and potassium secretion. Ultimately, when you have more sodium reabsorption, you have more water reabsorption, ECF volume rises. So please make sure that you know the renin, angiotensin, aldosterone cascade, specifically the functions of angiotensin 2 and aldosterone. Angiotensin 2 is a potent vasoconstrictor and does increase a little bit of sodium reabsorption. Aldosterone is a potent stimulator of sodium reabsorption, and thereby also increases water reabsorption. So both of these hormones, will work towards ultimately increasing water reabsorption, and therefore ECF volume increases. Really, that's all we'll talk about. But the other factor that comes into play is the ANP, as we talked, atrial natriuretic peptide. So in cases of hypovolemia, when ECF volume falls, you certainly don't want ANP being released, because ANP will inhibit sodium reabsorption and therefore inhibit water reabsorption. So in actual fact, what happens is that there's a negative feedback effect on ANP, and you will secrete less ANP in states of hypovolemia, right? Obviously, in the case of hypervolemia, you want more ANP being secreted, because ANP will inhibit sodium reabsorption and therefore inhibit or decrease water reabsorption as well, and that will bring down water content in the body. Before we start describing the pathophysiology of hypovolemia, let's just look at this particular diagram over here and see what happens in clinical dehydration, right, just visually. So in clinical dehydration, that's severe hypovolemia, we have decreased vascular volume. So the amount of fluid in the vascular compartment has decreased, essentially there's less plasma, and as a result, we'll look at the various steps that will now occur. Because we have overall decreased vascular volume and decreased interstitial volume, because as soon as we have a decreased vascular volume, there'll be less hydrostatic pressure and more water, and then the osmolarity is also increased in the vascular compartment. More water will be drawn out of the interstitial spaces, so there'll be a decrease in the interstitial volume. As the volume further decreases in the vascular compartment, it will also decrease the volume in the interstitial compartment. So there's a decrease in the interstitial volume as well. As you start losing more and more water, and the net result is there's going to be an increase in the osmolarity, right? That only makes sense because we are concentrating essentially everything further. And that's what these little dots over here represent. Those are the solutes, if you like, electrolytes, proteins, etc. So there's an increase in the osmolarity over here everywhere, essentially, in the vascular compartment, in plasma, and in the interstitial space. Now, because we have an increase in the osmolarity in the ECF, what's going to happen to the fluid within the cell? Remember, 2/3 of total body water is locked up inside the cell. What will happen is, because now we've moved away from homeostasis, it's no longer an equilibrium between the osmolarity in the ECF and the ICF. What's going to happen is that fluid is going to be drawn. It's more constant. The osmolarity in the ECF has increased. We'll start off with osmolarity in the cells being the same. So which way is water going to move? Water always moves from a less concentrated solution to a more concentrated solution. So water is going to move out of the cell into the interstitial space. And as a result, you're going to have cell shrinking, therefore a decrease in the intracellular volume, right? And that osmosis occurs because you want to maintain balance between the osmolarity in the ECF and the ICF. So the net result is that there is a decrease in the intracellular volume. The cells shrink. So that's the effect of clinical dehydration. Is ultimately it results in an increased osmolarity and cell shrinkage, right? And we'll see why that is important as well. Let me just go back and talk about edema as well. And here are the various causes of edema. So remember that in cases of edema, we have fluid retention in the body, typically in the periphery. Cerebral edema is even more severe, but we'll talk about that in the context of hypo and hypovolemia. So let's briefly look at edema, and this slide is very important. You should know the different causes of edema. A couple of slides back, we saw the various forces that operate in terms of normal capillary filtration. We have the main forces being capillary hydrostatic pressure, pushing fluid out of the vascular compartment, and then we have the capillary osmotic pressure bringing fluid back into the vascular compartment. We can ignore the hydrostatic pressure of the interstitial fluid and the oncotic pressure of the interstitial fluid. They are so small that we can ignore the forces. So essentially it's about the balance between the capillary hydrostatic pressure and the capillary osmotic pressure. Usually capillary hydrostatic pressure is a little bit larger overall than capillary osmotic pressure, so more fluid gets pushed out of the capillary than gets pulled back in. We did all this in ENP2. If that is allowed to continue indefinitely, then eventually all the fluid will be pushed out of the vascular compartment of the capillaries. But the excess fluid that gets pushed out, because capillary hydrostatic pressure is greater than capillary osmotic pressure, is ultimately drained by the lymphatic vessels. There are way more lymphatic capillaries than there are actual blood capillaries. So the excess fluid in the ECF, in the interstitial places, is drained by the lymphatic capillaries and placed back into the venous circulation. That's through the thoracic duct and the right lymphatic duct, remember. So that's a function of the lymphatic system, right, to be a big drainage system. And that's just because of the physical forces that are operating within the capillary. Capillary hydrostatic pressure is a little bit greater than capillary osmotic pressure. More fluid gets pushed out. That extra fluid is drained back by the lymphatic vessels. So that's the normal homeostasis that's operating in terms of capillary exchange. Now let's look at the various causes of edema. So in this case over here, it shows you this big black arrow is increased dramatically. So what that means is that capillary hydrostatic pressure has increased dramatically for whatever reason. Say it's malignant hypertension, so a huge increase in blood pressure for whatever reason. That's obviously going to push more fluid out of the capillaries into the interstitial spaces. The lymphatic vessels are no longer going to be able to keep up, and as a result, you have excess fluid in the interstitial spaces. That's edema. Fortunately, however, this rarely occurs because you don't just suddenly have a massive jump in blood pressure, so we can more or less ignore this particular cause of edema, right? That doesn't make sense. And we assume capillary osmotic pressure remains approximately the same. So this just doesn't occur very often, so we can kind of ignore it. A dramatic increase in capillary hydrostatic pressure, which is basically a dramatic increase in blood pressure. On the other hand, if you have let's look at this one over here, number D. If you have a tumor blocking the lymphatic drainage, then what will happen is that under normal circumstances, as we saw, more fluid is pushed out of the capillary than pulled back in, and the slightly extra fluid in the interstitial spaces is drained by the lymphatic vessels. If the lymphatic vessels get blocked for whatever reasons, now you're going to have fluid building up in the interstitial spaces. That's going to cause edema. So any sort of malignancy that targets the lymphatic vessels, and which is really most of them, that's going to cause edema over there. Or if you have any sort of surgery that damages the lymphatic vessels, that's also going to cause significant edema. This especially occurs in cases of mastectomy or radical mastectomy, where they remove most, if not all, of a breast, and they'll typically also remove the axillary lymph nodes at the same time. And when that happens, you've damaged the lymphatic vessels over there, especially the lymph nodes and the vessels that lead to the lymph nodes. And as a result, you can have significant swelling or edema on that particular arm on the affected side. So if the right breast is removed, then you can anticipate that the right arm will be very significantly swollen. You will have significant edema over there because the lymphatic vessels that drain the right arm are going to be damaged over there, right? So that's part D over here. If you have, and let's look at E over here, if you have states where you suddenly are not able to produce enough of the main plasma protein, which is albumin, and albumin is, I guess, drawn in these brown circles over here, tiny circles over here. So under normal circumstances, you can see over here we have albumin, quite a bit of albumin. And in this state over here, we have a decreased albumin content. So that's hypoalbuminemia, where you can no longer, for whatever reason, manufacture enough albumin. That occurs in states of liver disease, so liver cirrhosis, acute hepatitis, or even chronic hepatitis, where the liver is very inflamed or cirrhotic. The liver can no longer produce enough albumin. Albumin content in blood decreases or plasma decreases. And now what does that do? that causes a decrease in capillary osmotic pressure. Oops. Capillary hydrostatic pressure is the same, so water is still being pushed out of the capillary, but now capillary osmotic pressure has decreased dramatically because there's very little albumin in plasma, and so very little fluid is going to be pulled back into the capillaries. As a result, more fluid is left out in the interstitial spaces. Yes, some of it will be drained by the lymphatic vessel, but the lymphatic vessels cannot keep up. The lymphatic vessels operate very well under normal circumstances, but in this case, they're simply overloaded. So now you're going to have extra fluid in the interstitial spaces. Edema results. The other thing, which is rather rare, so the common causes of edema, as we mentioned, is decreased capillary osmotic pressure due to typically liver diseases, and that causes a decrease in albumin synthesis. You have lymphatic blockage, so that's very common. So D and E are very common. B, A is normal. B is very rare, some dramatic increase in capillary hydrostatic pressure. Now let's talk about C over here, where we have a increased interstitial fluid osmotic pressure. That doesn't really make much sense. The only way you have increased interstitial fluid osmotic pressure is if you have protein, a lot of protein in the... Actually, it does occur, so I'll take that back. And this is the most common, once more, is a blockage of the lymphatic vessels when you have a decrease in albumin content. And in this case over here, you can see those brown dots over here. That's an increase in albumin in the interstitial spaces. So how on earth would you get an increase in protein content in the interstitial fluid? Normally, the interstitial fluid is protein-free. It's essentially plasma, but without the proteins. That's what interstitial fluid is, because proteins are not filtered through the capillaries. The proteins are not allowed to move out of the capillary because of the basement membrane and so forth. So water can go through, electrolytes can go through, but red blood cells and proteins are not allowed through, right? That's in a continuous capillary. So how on earth would you get an increase in protein content in the interstitial fluid? Well, that can occur when the capillaries become leaky. And when do the capillaries become leaky? During states of inflammation, increased capillary permeability. So when you have increased capillary permeability, now you have proteins leaking out of the capillary. As a result, you have an increase in interstitial osmotic pressure, and more fluid will be pulled out of the capillary as a result. Normally we ignore interstitial osmotic pressure because it's almost zero because there's no protein. But now when you increase the osmotic pressure in the interstitial fluid, more fluid will be drawn out of the capillary. It results in edema. That's the main cause of swelling in inflammation, right? You have leaky capillaries. And so leaky capillaries doesn't just mean water leaks out. No, water leaks out more because the protein leaks out, and that's osmosis. You have an increase in osmolarity in the interstitial fluid, and water's going to follow, period. So that's what happens. So the three states that essentially give rise to edema is one, when during states of inflammation where you have protein leakage, increase in interstitial osmotic pressure, more water gets pulled out of the capillaries. Two, when you have any sort of blockage of the lymphatic vessels, now fluid cannot drain from the interstitial spaces, you have edema. And thirdly, and this is also very common, in any sort of severe liver disease, liver cirrhosis due to alcohol abuse, hepatitis, any sort of liver disease where the liver can no longer manufacture albumin fast enough, the albumin content in plasma decreases, there's a decrease in capillary osmotic pressure, less fluid drawn back into the capillary, that's edema. So essentially you ignore B, forget about B, because that just doesn't occur. Focus on C, inflammation, leaky capillaries, and increase in interstitial osmotic pressure. Focus on D, blockage of the lymphatic vessels, and focus on this E, where you have a decreased synthesis of albumin, typically due to liver disease. We are finally going to discuss the pathophysiology of hypovolemia. We'll start off with the etiology. So the various causes of hypovolemia, or the etiology, include GI losses due to vomiting, nasogastric suction, diarrhea, fistula drainage, and so forth. Secondly, we have third spacing. What's third spacing? Well, the first two spaces or compartments within our body that contain fluid or water are the ICF and ECF. The third space is the peritoneal cavity or the pleural cavity. So anytime you have fluid accumulating in this peritoneal cavity or pleural cavity, we call it third spacing. What that means is that water is no longer typically in the ECF, in the plasma, and so you have vascular depletion or hypovolemia. So third spacing can occur due to aside formation, pleural effusions, bowel obstruction, crush injuries, and burns. Third, we have inadequate intake, which is obviously self-explanatory. Fourth, polyuria, that can occur, for example, in diabetic ketoacidosis or DKA, where you have a lot of urine generation and hence a loss of water being lost through copious amounts of urine. That's polyuria. We also have sepsis that can result in hypovolemia. How? Well, that's pretty obvious because of the inflammatory process leading to increased capillary permeability that might cause third spacing as well. And then lastly, we have insensible losses. So these are evaporatory losses through the skin or the respiratory tract. Typically, under normal circumstances, we have 75% of the insensible losses occurring through the skin, so that's just simple evaporation, and 25% through the respiratory tract, that's loss of humidity in exhaled air. So now if, for example, you have someone who is vigorously exercising, they'll have increased insensible losses, but if they don't adequately replace that fluid loss, then they can land up with hypovolemia. It doesn't have to be vigorous exercise either. It could be in the case of, for example, a very elevated body temperature or high fever that can cause increased diaphoresis, and that's insensible losses. And if the fluid is not replaced, hypovolemia can result. The pathogenesis of hypovolemia, remember, pathogenesis means how does it develop. So it's very obvious when you have loss of fluid, you will end up with hypovolemia if the fluid is not replaced. So I'm just going to use this slide to remind you to revise a couple of concepts related to fluid homeostasis. We mentioned already how ECF osmolarity is regulated, or ECF homeostasis, so please make sure that you revise that. Also, you need to revise the function of the following hormones, the entire RAS cascade. So we're talking about renin, angiotensin 1, angiotensin 2, and aldosterone. We've covered this in ENP, so please make sure that you go over this again. It's in the textbook as well. Also, we also mentioned the role of ADH, or antidiuretic hormone, in terms of increasing water reabsorption or increasing water reabsorption in the collecting tubules of the kidneys. So that occurs, increased ADH secretion occurs in cases of hypovolemia, where you have a decreased ECF fluid and you have an increased osmolarity as a result. So it's osmoreceptors that get triggered. So please go through that a couple of slides ago. And lastly, in cases of, in this case, hypervolemia, you have ANP or atrial natriuretic peptide being released. So make sure that you understand its function. Essentially, it reduces sodium reabsorption in the kidneys, and thereby less water is reabsorbed as well, and you have more water excretion, so increased urine production occurs, fluid levels will decrease. So that's all the pathogenesis, essentially. Let's talk about the clinical manifestations of hypovolemia. We'll break it down into the organ systems. In terms of CNS findings, you have altered mental status, sleepiness, apathy, and eventually coma. How all that results is typically the result of either cell shrinkage or cellular swelling of the neurons. So in the case of hypovolemia, you typically would have an increase in osmolarity in the ECF because you've lost water. Essentially, everything's concentrated down. So now what's going to happen is that fluid is going to move from the ICF, from the cells, into the ECF in order to equilibrate the osmolarity. In either case, the neurons will shrink, and that results in these classical central nervous system findings of altered mental status and eventually coma, if not rectified. In terms of the cardiovascular findings, you have depletion in the vascular compartment, and that's obviously a decrease in plasma volume, and that can result in a reduced blood pressure, typically manifested at least initially by orthostatic hypotension and tachycardia, because when you reduce the blood volume, you have to increase the heart rate in order to maintain cardiac output, so tachycardia will definitely result in cases of moderate to severe hypovolemia. For the skin, you have poor skin turgor, hypothermia because of reduced vascularity of the skin, pale extremities for the same reason, dry mucous membranes, dry tongue, and so forth, right? These are only evident in cases of severe hypovolemia, so it's rather difficult to gauge hypovolemia based upon those clinical manifestations early on. We're talking about clinical manifestations related to the skin. Oliguria will definitely result, again, in moderate to severe cases of hypovolemia, so urine output needs to be measured, and if hypovolemia is not corrected, acute kidney injury can also result. In terms of treatment, which you actually don't need to worry about, we'll obviously it needs to be corrected, so you need to correct the volume deficit, and you first begin with isotonic solutions such as normal saline or lactated ringers, and then eventually you need to go to maintenance fluids. So frequent monitoring of the heart rate, blood pressure, urine output, and daily weights, as we mentioned previously, is essential. Urine output should be maintained at 0.5 to 1 mils per kilogram per hour, and that would depend on, as long as urine output is at that level, then hydration is adequate. And if there is also blood loss, then you need to replace the blood loss with crystalloids at typically a 3-to-1 ratio. I did mention that after the initial isotonic solutions, you need to start off with maintenance fluid, and the most common maintenance fluid is D5, so that's dextrose 5%, half normal saline. So that eventually is still an isotonic solution, and usually 20 milligrams of potassium chloride per liter is also given along with D5 half NS. Let's move on and talk about hypovolemia. So in terms of hypovolemia, we will start off with the etiology, and the etiology is pretty straightforward. It could be either iatrogenic, which is hopefully a rare case, because that essentially occurs due to parental overhydration, so during parental feeding or any such type of treatment. If it is not monitored carefully, then hypovolemia can result. More commonly, however, hypovolemia occurs as a consequence of various fluid retaining states. Typically, that would be congestive heart failure, which we'll talk about in Unit 8, nephrotic syndrome, which we'll see in PhD 2, liver cirrhosis, which actually we've already discussed, right? Because if you have liver cirrhosis, you're not making enough albumin, the plasma oncotic pressure will decrease, less fluid will be pulled back into the capillaries of the vascular system, more fluid will be left out in the interstitial fluid, and as a result, fluid will be retained over there, and hypovolemia can occur. End-stage renal disease is also another very common cause of hypovolemia. So remember, we'll talk about congestive heart failure. That's typically left-sided heart failure, which causes fluid or blood to be backed up in the venous circulation. And over here, if fluid gets backed up in the venous circulation, you have increased hydrostatic pressure, and that will push more fluid out of the capillaries into the interstitial fluid. That can result in edema and hypovolemia. Nephrotic syndrome, just very briefly, occurs because you have proteinuria, so you lose a lot of protein in the urine. As a result, albumin content of plasma will decrease, and just as we saw in liver cirrhosis, it doesn't really matter what the etiology is of a decreased albumin content in plasma or serum albumin concentration. Whatever the case might be, if you land up with hypoalbuminemia or reduced serum albumin levels, then edema and hypovolemia can result. So nephrotic syndrome is basically a loss of albumin through the kidneys. So now there's less albumin in blood, and we already mentioned how the process occurs in the case of liver cirrhosis. So those are the main etiologies for hypovolemia: the fluid retaining state, congestive heart failure, nephrotic syndrome, liver cirrhosis, and ESRD. Let's do the pathogenesis, which really is the same thing as before. It's the same duplicate slide from the hypovolemia, where now we're again just revising these concepts over here, so I'm not going to go through this again. Pathogenesis, remember, is how does that disease or disease state arise, and in the case of hypovolemia, it's because there's too much fluid, essentially. But you have to know how fluid homeostasis actually occurs, so please revise all these concepts. In terms of the clinical manifestations of hypovolemia, you have several, including a weight gain, which would be the most obvious one, right? So that's why it's very important to do daily weight gains as well. Peripheral edema, as we mentioned, in all those fluid retaining states, such as congestive heart failure, nephrotic syndrome, as well as liver cirrhosis. Ascites can also be, that's the third spacing that we were talking about, that can occur. That's also a hypovolemic state. Pulmonary edema, meaning fluid in the lungs, excess fluid in the lungs, that can also be a manifestation of hypervolemia, where you have increased pulmonary hydrostatic pressure, and that can force fluid out of the pulmonary capillaries and result in fluid being retained in the lungs. That's pulmonary edema. As a result of hypovolemia, you would see jugular venous distension as well, especially if congestive heart failure is the cause of hypovolemia, one of those fluid retaining states. So you have increase of plasma, so an increased plasma volume, and as a result, the jugular veins will be distended, especially in the cases of congestive heart failure where the blood is not being pumped properly from the left side, so that's left-sided heart failure. So blood gets backed up in the venous circulation, especially prominent in the jugular veins. So you can quite easily observe that in severe cases of congestive heart failure. Pulmonary rales occurs as a result of the pulmonary edema, and if you have a real expansion of the plasma volume, now you can anticipate that hematocrit levels and albumin concentration will also be low because you simply have so much fluid, everything gets diluted down. In terms of the treatment of hypovolemia, which you don't really need to worry about, it consists of fluid restrictions, judicious use of diuretics in moderate to severe hypovolemia. One of the diuretics commonly utilized are the loop diuretics such as Lasix or furosemide. And lastly, you would also monitor urine output and daily weights.
In summary, please remember to revise the fluid homeostasis, specifically knowing the various compartments, the ICF, the ECF, which is subdivided into plasma and interstitial fluid, how osmolarity or osmolality is regulated, the various hormones that are involved, all that we covered in NURS 1020 and P2. Please also revise capillary exchange from NURS 1020 and P2, the various causes of edema we covered in this particular lesson, and then we went over the pathophysiology of hypo and hypovolemia. In our next lesson, we're going to look at the various electrolyte imbalances. That's going to be part 2. Thanks, have a great day, bye.